In this video, we are going to work on worksheet number 6, which is about the sections 9.3 and 9.4. These sections are about tangent planes and linear approximation for 9.3. So the first question here is about finding the equation of the tangent plane to the given surface at the specified point. So now that we have the point and we have the formula of the function, we're going to find the partial derivative with respect to x and also with respect to y. So when we're finding the derivative with respect to x, the first term doesn't have any x in it. The second term has x and also the third term. So the derivative would be negative 4x plus 1. And we would evaluate this at the point x equals 2 because there is no need to write y value and z value. We only have x value here. If we plug in 2 here, we would get negative 7. For finding the derivative with respect to y, we only consider the first term because this is the only term that has y. And taking derivative with respect to y gives us 6y. And y here is negative 1, so the answer would be negative 6. Following the formula of writing the tangent plane, which is z minus z sub 0 equals z sub x, which is partial derivative with respect to x at a point a and b, times x minus x sub 0 plus partial derivative with respect to y at a point a and b times y minus y sub 0. Following this formula with the information that we have here gives us z minus negative 3 because we know that this is x sub 0, this is y sub 0, and this one is z sub 0. Partial derivative with respect to x at the point is negative 7, x minus 2 here, plus partial derivative with respect to y at the point is negative 6, and y minus negative 1 will be here. So if we simplify this, we would have z plus 3 equals negative 7x plus 14 minus 6y. Inside the parentheses would be plus 1 times negative 6 gives us negative 6. So if we subtract 3 from both sides, we get z equals negative 7x minus 6y, 14 minus 6, which is 8, and then minus 3 would be plus 5. This is the equation of the tangent plane. Same idea for part B. We would find the derivative with respect to x. We would find derivative with respect to y. For the first one, since this is ln of x minus 2y, we would find the derivative of the inside, which is 1, when we find the derivative with respect to x, over whatever we have inside. At the point when x equals 3 and y is 1. So in this case, it will be 1 over 1, which is 1. Finding the partial derivative with respect to y gives us negative 2 as the derivative of whatever I have inside over x minus 2y when x is 3 and y is 1. And the answer would be negative 2. Following the same formula as we had here, we would have z minus z sub 0, which is 0 here, equals 1 times x minus 3 plus negative 2 times y minus 1. So left side would be z, the right side is x minus 3 negative 2y plus 2, and after simplification that would be x minus 2y, and negative 3 plus 2 is negative 1. Let's do number 2. Explain why the function is differentiable at a given point. Then find the linearization of the function f of x and y equals x square root of y at the point 1 and 4. So we're going to find partial derivative of the function with respect to x, which will be square root of y. And when the point 1 and 4 is considered, that would be square root of 4, which is 2. We're going to find partial derivative with respect to y, which will be x over 2 times square root of y. I usually say that find the part that has the variable in it, in this case square root of y. So the derivative would be 1 over 2 square root of y. And since we have x here, we would multiply this by x. This is why the partial derivative with respect to y is going to be x over 2 root y, root 2 of y. And this will be evaluated at a point as 1 over 4. Before writing the linearization, we need to know that these functions are differentiable. So based on the theorem number 8 in the lecture slides, we know that both of these two functions that we have as the partial derivative are continuous under domain. So when y is positive, because the domain of square root of y should be a positive number, we can say that according to theorem 8, f is differentiable at the point that is given to us. Once we know this, we're going to write L stands for linearization of x and y, which will be approximately f of the point that is given to us plus the combination of partial derivatives as f(x) of the point times x minus x sub 0, which is 1 here, plus partial derivative with respect to y at the point times y minus y sub 0, which is 4 here. So linearization is approximately, in order to find f of 1 and 4, we're going to plug in these two numbers. That would be 1 square root of 4, which is 2. So here we write 2 plus partial derivative of f with respect to x at the point 1 and 4 is 2 times x minus 1 plus 1 over 4 times y minus 4. So we can simplify this as 2 plus 2x minus 2 plus 1/4 of y minus 1, which will be 2x plus 1/4 of y minus 1 as the linearization function here at the given point 1 and 4. Let's do number 3. Number 3 says verify the linear approximation at 0 and 0. So this linearization is given to us and the question wants us to verify this. So we assume that f of x and y is given to us as 2x plus 3 over 4y plus 1. Or we can rewrite it as 2x plus 3 times 1 over 4y plus 1. And we're going to find the linearization of this and linear approximation. And we would compare to 3x plus 2, 3 plus 2x minus 12y to see if they are the same. In order to do that, we're going to find partial derivative of f with respect to x of x and y. That would be the derivative of the part that has x in it, which is 2 times the rest, at a point when y is 0, because the point is 0, 0, so y is 0. And plugging in 0 gives us 2. Partial derivative of f with respect to y, derivative of the part that has y. So we just copy the first part. It doesn't have any y in it. It works as a coefficient. But the next part is a quotient. So negative 1 over 4y plus 1 squared is the derivative. You can find it using quotient rule. You can find it using 4y plus 1 to the power negative 1 and use chain rule for that. Either is fine and you would get the same answer if you do it correctly. So plugging in x and y as 0, we get negative 12 here. And f of 0 and 0, the point that is given to us is 3. Putting them together as linear approximation, f of x and y would be approximately f of 0 and 0 plus partial derivative at this point times x minus 0 plus partial derivative at this point with respect to y and y minus 0. So the linear approximation of this function is going to be 3 plus 2 times x minus 0 minus 12 times y minus 0, which will be approximately 3 plus 2x minus 12y, which is exactly the same as the function that is given to us. So this linear approximation is valid. Number 4. A function is given to us with the information that f of f partial derivative with respect to x, partial derivative with respect to y are evaluated here, and we would use a linear approximation to estimate another point which is close to the given point. We know that 2.2 is close to 2 and 4.9 is close to 5. So following the formula that says f of x and y as a formula for linear approximation will be f of the point plus partial derivative at that point times x minus x sub 0, which is 2 here, plus partial derivative with respect to y of the point times y minus y sub 0, which is 5 here. So according to the question, f of 2 and 5 is 6. Partial derivative is 1 with respect to x times x minus 2. Partial derivative with respect to y is negative 1 times y minus 5. Multiplying them together, we get 6 plus x minus 2 minus y plus 5. And if we simplify, we get x minus y plus 9. So using this, that is the linear approximation of the function that we had information about, we're going to find this here. So f of a point near the given point will be found using the formula that we already found here as approximation. That would be x minus y, which is 2.2 minus 4.9 plus 9, which will be 6.3 here. Number 5. Okay, please pause the video, read the question, and then listen to the solution. First of all, I would like to rewrite it as 2.65 m to the power 0.66 plus 3.5 times m power 0.75 times 1 over v. It helps us to see the variables here. So as the first step, in order to write the linearization, we're going to find partial derivative with respect to one of the variables, which is m here, at the given point, which is 408 here. So following the formulas of derivative, for the first part will be 2.65 as the coefficient times the power times the variable itself with 1 less. It means 0.66 minus 1. Plus the second part, 3.5 is the coefficient, 1 over v is the coefficient. But finding the derivative of m to the power 0.75 gives us 0.75 times m to the power 0.75 minus 1. Simplifying these gives us 1.749 m to the power negative 0.34 plus 2.625 m to the power negative 0.25, 1 over v. At the given point, which is 408. 400 is m and 8 is v. So using calculator, this will be approximately 0.301 kilocalorie over or per gram. What about the second part? It will be partial derivative with respect to v at a point. So first term here doesn't have any v in it, so the partial derivative would be 0. The second part, we know that partial derivative of 1 over v would be negative 1 over v squared. So we would write the whole thing here as negative 3.5 m 0.75 times 1 over v squared. Or if it helps, you may write the negative here. At the point 408. Using calculator, this will be negative 4.89 kilocalorie per kilometer per hour. Using these two and the amounts that we found for this, we're going to follow the formula of linearization, which will be L of m and v equals e, the amount, the evaluation of the function at the point 408 plus the partial derivative with respect to m at the point times m minus 400 plus partial derivative with respect to v at the point and v minus 8 here. So it only needs to plug in for these parts here. When you plug in 408 here, in order to find E of 408, you would get 177 plus 0.301 times m minus 400 plus negative 4.89 times v minus 8. And this would be approximately 0.301 m minus 4.89 v plus 96.